So far, in all the almost in all the machine learning classes except reinforcement learning, you might have learned about you have data and you have labels, and you somehow learn and train a model. You talk about what's going to be there inside the model, what kind of model is going to train, about the training protocol, loss functions, network architectures, and everything. Now we're certainly talking about unsupervised learning, and which somehow implies that you don't have labels. So how many of you are familiar in some form, remotely or not, about unsupervised learning? Can you raise your hand? All right, that's good. Okay, so basically it refers to you do not have labels in a coarsely speaking. So what it leaves to you is that, okay, if you don't have label, then what are you learning for, right? So far you see that, okay, I have data and I want to map it to the label, and now I don't have label, then what do I do, and what does it mean by learning? So whole idea of unsupervised learning comes from the fact that supervised learning works great. So first of all, people were trying to make the supervised learning work well, because it was not easy to make, for example, like millions of images from ImageNet, 1,000 classes to really classify with 90% accuracy. So now it works quite well. You can see this particular plot that especially with the beginning of deep learning somewhere here, that it's just working better and better, and it's almost saturated. In some sense, that means maybe there's not much of incentive to improve the classification accuracy of ImageNet anymore on the classical setup of 1,000 classes. Okay, then since supervised learning works well, and that's why we are here learning about the learning, that's not only about classification problem. If you want to detect people or objects, if you want to semantically segment images, it means if you want to classify or know about every single pixel and its semantics in the image, it works great. And you can even find out the instances of people that you can basically, instance wise segment them, who is where, basically, right? So all this works great. The problem is that I can move it here. Problem is that supervised learning requires a lot of data with labels. Labels are the key, because labels means that you need to annotate mostly manually. Since you need to annotate manually, it's going to be super expensive. So whole game is all about, if you want to solve any particular task, because last time we already discussed about that, you can train models or you can have algorithms or methods, they eventually get customized to certain problems, right? Then you have so many problems, then for each of the problem we require different kind of data to be collected. And not only that, you also have to annotate each of them. So although it works, it's not so practical to just use it. Therefore, the battle for training data can be nasty. So you can actually have data in some form, but not the label, sometimes not even the data. So there's a big mess in practice. That's what it means. So if you look into how do we learn, we don't really learn from bunch of images, a bunch of data that comes with annotation. If you look at babies, they just observe the world and figure out something. Of course, they don't know what it is exactly. They do not know, let's say, they can see, in this particular example, the baby can see different colors of the ball, but baby still does not know which one is red, which one is green, which one is yellow. So there are something called semantic tags that are associated with the visual world. And there's something without the semantic tags, you can still understand. The first part of understanding, just observing and understanding, it's called some form of representation. For example, if a baby sees a cow and cows after the cows, already understand that it's an instance, is some kind of things that moves, can move, and it is whole thing as one, right? The whole cow is one, but still doesn't know it is called cow. So you don't need to have the label of the cow to have some kind of representation of the cow, so that when somebody, the mother tells the baby that, okay, this is a cow, instantly it can be learned to associate the labels. That's the one kind of representations that you can have of the world, and that's what we are interested generally in learning unsupervised. And other aspects is, it's not only about the instances, it's more about the object persistence. You can see this video. So this chimpanzee actually expects the object to persist there, magic not to happen. And that's not because somebody told it, right? It just knows that it's supposed to be there. You don't need labels. You just observe the world and understand how it's supposed to behave. And the mere fact that the world is not behaving as per expected, it becomes funny to him. Well, you can keep on watching this. So idea is that there is much more than just associating labels to the world that we observe from the vision point of view, that can be learned without requiring labels. So this is a slide from Jan Lugun. You might know him already. So if we consider whole learning paradigm to be a cake, so main part of the cake should be unsupervised learning or self-supervised learning or predictive learning, in its sense that the main part should be unsupervised learning. Then there comes the supervised learning on top, the creamy part of the cake maybe, and then the cherry on top of the cake is what reinforcement learning would be. So I personally don't have anything against reinforcement learning as such, like Jan Lugun, but what I'm trying to lobby here is that the main part of the cake, or the whole main part of the learning, has to be unsupervised. That's also quite a lot of common belief among the researchers nowadays, that unsupervised learning, the examples I gave you before, the baby could learn, the chimpanzee could learn what to expect in the world, and those kind of learning takes in some form of the abstractions that can be learned before getting the access to the labels, and then labels can be later on used for supervised learning. So this is just one case against reinforcement learning, because you have, well, maybe it's not a nice thing to say, but you had the course and you are doing assignments in reinforcement learning, and reinforcement learning is definitely going to be important, but not going to address the problem of unsupervised learning. That is mostly because our world runs in real time. You cannot go faster than 1 second per second. And that's the problem, because in the simulated world, for example, of the Go or the chess or anything, that you can just fast, like fast, do it much more faster, and then can learn in the game environment. But in the real world, you cannot just go faster than time. And then a single mistake in the real world may just kill you. Therefore, reinforcement learning may not really the way to go, to have some kind of representation of the world, just like the chimpanzee or the baby have, before actually associating the semantic tags to things. Well, so to start, this slide is not to be explained just to scare you, that of course there are so many things to understand in machine learning, that we talk about deep learning, reinforcement learning, unsupervised learning, Supervised learning, and then it just branches out and just too many things to understand. Furthermore, there's too many buzzwords that we talk about: data distribution, self-supervised learning, classifiers, weak supervisions, concept of dimensionality, knowledge transfers, inductive biases, features. So it's a big mess. So the point of view of the unsupervised learning somehow tries to simplify this big mess of things. At least that's the hope. That let's just try to represent the world in some form of abstractions before associating even these kind of tags about how things to be learned. Things need to be learned in some form of abstractions beforehand, and then bring all these kind of learning framework and then all these kind of tags. So let me simplify things for you in that regard. So in this particular example, if I'm given bunch of images of dogs and cats, very easy example, it doesn't have to be neural network here. So on the left, it has the image space, this image space. Default representations are very high dimensional, the course of dimensionality are, and then there itself, it might not be an image, it might be different form of data. That's where you learned about geometric deep learning and stuff like that. So data will eventually live in this kind of high dimensional space. And then you can try to map that, not necessarily using a deep neural network. You can try to map that into some abstract space, and you might be aware of this feature space. Let us learn features. Let's learn features, and that hopefully will be useful later on. And the question is, to learn that feature, do I need to have the labels? And the answer to that is no, actually you don't need to have you don't need to have labels to learn the features. But then how do you want to learn the features to those data points? It's like, first of all, it has to be somehow in low dimension, because often your data comes in very, very high dimension, right? Just let's map into some low dimension where whatever semantic tags you are going to associate later on will be meaningful. Of course, that's the tricky part, right? Because I do not know the definition of the semantic tags beforehand, and I just suddenly expect that some kind of mapping that takes place from the default representation to semantic representation or some low dimension representation would be meaningful. But essentially, we are hoping that if you map it to this low dimensional space, now here you can do more of the statistical modeling about, let's say, even you can train a linear classifier to classify between dogs and cats, because the data already lives in that nice form of the in the nice form of the space. So you just want to learn this particular mapping. In this particular mapping, doesn't have to deep neural networks again. Here comes all kind of inductive biases, all kind of network designs, everything that you are learning from the raw data into mapping to space is where you want to bring all the knowledge that you have, how images need to be understood. For example, there was one particular paper, it does what's there in the randomly initialized neural networks. What you do is you take a convolutional neural networks and apply on the images and just extract features. You don't train the weights at all whatsoever. And then you train a classifier afterwards on the extracted features, extracted using a random network. That already happens to work quite well. It's because it's a convolutional neural network. One of the reasons is because convolutional neural network, right? So there has been so many thoughts put into designing the network. The inductive biases or the prior about the data has already been integrated into the network design process, and hence even if the weights are random, the features are not completely random. The mere fact that the convolution operations are done is not complete random operations, right? So even if you do that kind of operations using the random weights, the features that you obtain is not completely random. You are already injecting the bias about how it needs to be seen, right? The inductive bias is about in the formal convolutions. Similarly, other things can be done. If you are learning from the temporal data, you are using LSTMs or RNNs, right? That's also about how data needs to be processed. So in the form of the network architectures, some biases could be injected to understand that how data needs to be understood, right? So that thing can be done here. Once all those kind of knowledge that you have about the data, as a human being, that knowledge that you have about the data, once been injected, and then maybe some form of learning can also take place, eventually to map that input data into some space where now the statistical molding of the data would start becoming meaningful. Because in this input side, this data lives in like billion dimensional space, and where if you try to make any kind of modeling of the probability distribution of data, that really becomes quite pretentious. Whereas here it already becomes quite compact and then semantically meaningful, and there if you try to make distribution modeling or any kind of classifiers you are trying to train, and it becomes much more meaningful on this side. And the whole, at least one strain of the unsupervised learning is aiming to map the high dimensional data into low dimensional data to extract visually meaningful, for the images, visually meaningful features, and accordingly any data that you are processing, they are meaningfully in that regard. So essentially there are only two things. One thing is about the representation. Once good representations are obtained, good features are obtained, then you want to do the label assignment, that what it is up to us, right? And the label assignments will come can come in the much more simpler form. So current trend of doing unsupervised learning, this slide, I know you have seen it before, and this slide you will see everywhere, is basically you take one image and then augment it in two parts. On the left, you can see that the dog has been augmented in two parts and pass it through a Siamese network. Siamese network basically is the same convolution network. Doesn't have to convolute, same network, repeated by sharing weights, and you extract features. Since these features supposed to be coming from the image with the same semantics, are both from the dog, therefore you try to minimize the distance between them. And on the other hand, here is a dog, here is a chair. Features that you obtain from the chair and features that you have obtained from the dog, they should be different. It's a very simplistic, very naive approach, that all you are saying is that if I take two crops of the same image, assuming that I'm just interested on these classes of the images, right? So they must have the same features, otherwise not. That's what the loss function I can derive is called contrastive loss. If you use that, let's see what happens. So here you can see, let's minimize. Here you can see that supervised learning obtains some accuracy here around 79, and these are unsupervised methods, and this obtains somehow similar to supervised method. This is kind of pretentious, right? Because what I'm saying is that now unsupervised method that doesn't use the label also does as good as supervised method on ImageNet top 1 classification accuracy. It's like no, that's not really true. It's not that it classifies the image correctly. What we are doing, what has been done is that it learns the representation that when used by a linear classifier, just a linear classifier, like it's not deep, just a linear classifier, one fully connected layer to classify. Now at that time you will use the labels to classify. That representation will be as good as the representation that you would have learned using the supervised method. So one is that you are learning end to end, right? So you have the labels and it's backwards all the way through. Other is you just train this CNNs to extract the features. Once the features been extracted, Now you use the labels to train just a linear classifier. This time somehow you're training to assign the labels once the good form of the representation already been obtained, right? And that's how the unsupervised learning methods and supervised learning methods are compared. So here basically you are saying that if two patches of the image come from the same ones, it's the same semantics, otherwise not. That can be easily implemented, like few lines of code. This is just to show you that this implementation is quite easy. If you want to implement, and you can easily access the source code. This is one of different network than the one visualized here, but in few lines of the code that you can simply implement, and it actually does extract question-like features for imaginary classification. So this is a fact that everything in the universe is either a potato or not a potato. Well, so basically the whole idea is that the image that once you crop is either the same image or not the same image, and that's where the contrast bit begins. So if you have any question so far, you can ask me before we proceed.
Hello? Okay, I don't know if I have understood correctly, but let me try to question you. So if you are already using the convolution neural network, isn't it similar to supervised learning? Because filters in the convolution network, I think they are developed by comparing it to the outputs, right? The values in the convolution network filters. And they are actually developed beforehand by comparing with the outputs. And if we are using the same filters in this unsupervised learning, isn't it just same like the supervised learning where we have already assigned the weights?
No, weights are random.
But in supervised learning, the weights are generated, right?
Yes.
And
in unsupervised learning also you start from complete random weights. You don't use the weights from supervised learning. So the whole thing is that you could have processed in various ways, right? But in convolutions, the idea is you can actually share the parameters of the convolution across the operations, right? And it's just not random coincidence. It's been thought through that this makes sense to do it, right? Because in image, you cannot distinguish which path comes from where. And that's decision been made by humans that, okay, it is okay to do. And that's where the inductive bias comes into picture. That's the one part of the designing the CNNs, right? The other side, the question, if it clarifies that in unsupervised learning, we start by completely random weights and then try to learn the features so that the features of two crops of the same image are the same, right? And then features of two different images are completely different. That's the idea. And that's the only assumption that's been made. Yeah.
Understood.
And like, if there is no label, then how is the learning supposed to happen if it is only random initialization? How will know that the features actually represent the data? And if there is no back propagation, and if the network is not learning, then
there is a backward propagation that minimizes the loss. That when you have features from, basically what happens is that when you say this attract and repel, so attract means you compute some kind of distance between these two features and tries to minimize. And then you compute the distance between features from the dog and from the chair and try to maximize. You have these loss functions now, and you just back propagate the gradient from these loss functions. So it's still learning. And so that now at the end of the day, the features from different crops of the same image, they turn out to be the same. And features from different images, they turn out to be different. And then they have to somehow self-organize themselves, the features, right? And so it happens, right? They end up self-organizing themselves in a quite nice way, to the point that you can now simply train a linear classifier and perform as good accuracy as that of supervised learning. That's kind of magic. Can you get the mics? Or also speak loud for me at least. Speak louder.
We are training on same patches of in patch of same pictures for Chinese network. And if you want to classify new dog, how does that work? If you are training on same patches and not different level, different.
So what happens is that you will show eventually, let's say we're training an image net, right? You will eventually network gets to see all the image from image training setup image net. Okay. So network will eventually see, and then it has to make this trade-off that for any image, any two crops of any image that you pick, the features have to be same, right? So that's what the criteria that you're putting forward. So what it ends up doing, it ends up grouping all the docs together. Because the idea is that there are many more images which are not dogs than images which are dogs, like the potato example. So many then what it does is that it benefits by clustering the dogs together, because everything else is not a dog, right? And then there are many more images that are not dogs, thereby pushing away not dogs and bringing the dogs together. Happens to be some form of optimal solution. It's because eventually it has to bring things together, right? And then it doesn't do crops, but you don't know how these crops are going to look like. So then eventually it can only infer or learn or minimize the loss properly only by bringing all the images from the same class together, so that later on it doesn't have to worry, right? You can just keep two patches. It's immediately understood they must have similar visual information, therefore it will still minimize the loss. Yeah.
As the model learns more, does it also learn not to pick just a different picture of another dog to repel against and pick something like completely random? Or even in the later stages, is it still just picking a different image regardless of what category it belongs to?
So if I understand correctly, so what happens at some point in time, I think that your concern is that what happens, there are one dog on one side and other dog on the other side, right? So eventually you are asking it to push apart, and that's one of the very paradoxical way of training now, because if you pick a chair and the dog, it's fine because they are different, and once in a while you end up picking dog and a dog and then just ask, okay, they have to be different now. But the probability of picking two dogs together in this huge data set is very, very low, right? Whereas probability of taking dog and not a dog is very, very high. Therefore it ends up being some kind of optimal choice of bringing the dogs together, because you don't get penalized so much, right? In a grand scheme of training, that's how it happens to work.
So my question was, the act of bringing the dogs together, does that happen through human input, or does the model?
Just the model does that.
Does that? Okay.
It just automatically brings that, because it also has to learn to bring the features of two paths to the same image together, right? And doing that particular tension will eventually bring all the dogs together. Turns out to be the case. Anything more? Okay, maybe then we can continue. So what we do not learn today is that what we're trying to learn first of all is that we are trying to somehow train machines to learn just like humans do, right? That's what the motivation of unsupervised learning is coming into picture, that it somehow does learn the way that we learn. The previous examples like I showed you, but we do not really learn by augmenting images. Yeah, and then everything is not just about dogs and cats or 160 classes of mushrooms and things like that. I mean, in some regard, that of course at some point of time classifying ImageNet and 1,000 classes was challenging problem, but now it's not anymore. And using that maybe is not suitable anymore. We need to go for more difficult problems, and then showing that, okay, just augmenting images on ImageNet is actually good for feature learning. Maybe it's not the right way to go, and people mostly agree, because taking two paths of the images, asking them to similar, otherwise not, is just too naive for understanding complex concepts. So what the way human learn, that's how we want to mimic for the machines too. And there are different kind of paradigms, and one of the paradigms that is popular is in natural language processing, which is quite successful one, where you take text and remove the parts of the text. And then let's say, even if you have to do fill in the blanks, right? And then we have to infer based on the context and fill in the blanks. That's how we infer, and that's how we need, for that we need to understand the context. We need to understand what is there all out there, and then only we can meaningfully guess what do we fill in the blank. And this turns out to be quite successful unsupervised learning technique in natural language processing. And you can see on the left, that's the example that you can mask out your modes and ask it to predict. Since you have sentences, complete sentences beforehand, you can supervise. But now it's supervised, it's not completely unsupervised. That's why it's also called self-supervised, right? So you have the labels now, but these labels are created by removing the parts of the data itself, right? If you draw that parallel to images, because then what are the words in the images? It's kind of not clear, right? And you can say, okay, I can remove some parts from the image and ask it to reconstruct the image. And well, it doesn't, this particular one doesn't really reconstruct quite the same, but does reconstruct meaningfully, right? That's the whole point also about the masking here, that it does reconstruct meaningfully. And to do that, you have to understand in some form the content of the image. And that's what brings us to the representation learning. If you go not only on the image, but in the video, what you do is you provide a few frames of the video. Let's say you show 1 minute long video, and then ask what's going to happen next in 1 second later. For that also you need to understand what is happening, right? And then only you can make a predictions. Okay, now since all these things are happening, and this is what's going to happen after 1 second, and that's how you can self-supervise your network to extract the features, and therefore you can use those features later on for understanding task. This is not what we will be learning today, though. What we will be learning today will be by more interacting with the world. That's just the playing with the data in some form, right? But why don't we just interact with the world, but not in the reinforcement learning settings though. To interact, that we move in order to see, and we see in order to move. I mean, I come from computer vision background. For me, everything is vision, so my tone might not be very accurate from more broader machine learning perspective. Excuse me for that, but that's from here on, at least, that we'll mostly talking about the vision perspective of unsupervised learning. So essentially, that if we didn't have to move, there was no need to see, because you cannot move anywhere, right? So there's no point of seeing. I mean, if only if you can do some things, therefore intelligence matters, options matter, right? If you could not make any choice, then options would not matter anyway. And we move in this 3D world, that the world that we live in, and there we form some kind of map of the 3D world, and that's where we move and map, right? And then we interact with that 3D world. So we do some kind of 3D world mapping, where we move and interact, and then that's what eventually allows, well, one way we see and then map and then move. And you can say in the other side too, that since we can map and move, therefore we see. And this is the phenomena that takes place. Therefore, we move in order to see and we see in order to move. So I just want to give you one example that when it's not necessary, that the sea squirt is actually a like amazing little creature that lives in sea. When it's young, it's very vibrant. It goes everywhere, finds food, lives happily. Later in its life, it chooses to settle down in its own sense of settling down. But it finds a rock or a coral, it mounts itself there. So once it mounts itself there, it does not have to move. It will not move. And then the body parts of the sea squirt has not been developed yet to get the food. Therefore, first thing it does is it eats its own brain to survive. So that means if you settle down, then you are not using your brain. No, that's not the point. So whole point is that that if you do not have to move, then you don't need intelligence or the brain. That's why trees don't have brain, right? Whereas all the animals, they have brain. And they have different level of intelligence. Okay, I don't want to say that trees are not intelligent, but not the intelligent the way we understand. So that's how this particular animal does. It means that if you really want to understand the world, derive the intelligence in self-supervised or unsupervised fashion, then your system needs to move, and that most likely will not be in the form of reinforcement learning. That's where I say that we'll not be talking about that either. Rudolfo Linus has famously said in his book that a nervous system is only necessary for multicellular creatures that can orchestrate and express active movement. So if you are training your model that learns, then that also somehow has to move in 3D world. But then to act, you need to do the mapping of the scene, you need to understand, and you have to somehow localize there. And then to localize yourself is basically to interact, localize, map everything that you need some form of understanding, and then all things they come all together. So now if you can map and localize in the scene, does that also help to understand? Asking back the same question that we see in order to move and we move in order to see, right? So today's talk is about doing unsupervised learning to move and to map. And if we can do that, and hopefully we can learn the kind of representation that we are willing to learn beyond just doing augmentation of the images. So when I say localization, it's going to be about camera motion in the form of 6 degrees of freedom, 3 rotations, 3 degrees of freedom of the rotations, and 3 of the translation. When I say mapping, is about the 3D in the form of the depth map. So when you have the image, you also infer that how far the objects things are. And then, so we want to do this thing because the unsupervised motion and 3D needs to be learned jointly. And once we do that, it's the time to dance. No, so it's more about on the left is the video, RGB video. On the right is the depth prediction. Right? And then what I'm saying is that one can do this unsupervised. Actually, it's not very surprising. I'm just maybe trying to make it a little too dramatic. So one thing is that you don't need a neural network to predict depth from multiple views. You can just do mathematical computations, right? Now, what we're trying to tweak around is that, can I actually train a network that predict the depth from single view, which can be supervised using the framework that I would have used anyway otherwise if I didn't have my network, and thereby self-supervised. So I'm not clear here. Okay, so whole idea is that I could have, if I'm given two images, I don't know, if I'm given two images, I can always reconstruct. Okay, or almost always reconstruct. So I can reconstruct from two images. But what if I given only one image? And say I'm asking the reconstruction from one image, and for that you require understanding, because you cannot reconstruct from one image. For that you need to learn, for that you need to understand, right? So therefore you give only one image and ask your network to predict the depth, and then cross check if that depth is correct or not using the other image. Because using two images I could reconstruct anyway. Just like when I have a video, right, I have all the frames, right, but I just don't show the one from the future and ask it to predict. Similarly, I do not do the reconstruction from two views. I assuming that I have the reconstruction from two views somewhere, I keep it somewhere, right, I could have obtained, but I only give partial data. It means only one frame, and ask it to predict the depth, and now I supervise for with that depth. So things I could have done with the more data, I am asking my network to do with the less data, and for that it needs to understand the data itself. Otherwise it has no other choice, and that's the idea we are going. So in the unsupervised learning of this erasing the text, erasing the parts of the image is also that, right? I have the data, it's not that I don't have, I just don't show it. That's the trick. The trick is that I have the data, I don't show it, and I ask it to fill in the blanks in some form, right? Here what we are doing is, if I have two images, I could have reconstructed from two images without using the network anyway. So let's say I reconstruct the 3D, but I only give one image as an input, and I ask it to predict what I have computed using two images. And for that, the understanding would be necessary. All right. So I don't know if you have seen this, chickens always jerking their head like this. Can anybody tell me why do chickens jerk their heads? Anybody interested to answer this question? Why?
I think for the equilibrium.
For the equilibrium?
Yeah.
Maybe. You're saying something. How does that help?
Focusing on the target.
How does that help? Maybe if somebody sticks
Yes. It sees something, then
of the target.
it have to target how far it is or something like that.
But then how does moving the head will help?
I don't know.
Okay, that's fine, that's fine, that's fine, that's fine.
You get depth perception. I mean, it's the same way we perceive. It's the same way humans perceive depth by having two.
Yeah.
And the angle we make with the target gives us some intuition on how far it is.
Exactly. One thing that you didn't realize maybe is chickens, they have two eyes, but on two sides. Unlike us, we have two eyes on the same side, right? Both the eyes that we have can see the same thing. Therefore, it forms some kind of disparity like this. When you go to 3D movies, the old days especially, or even the nowadays, if you don't really use the glasses, right? You see some form of disparity like that. And the idea is that the red channel is supposed to go on one eye here, and then blue is supposed to go on the other eye, and therefore create the disparity, and hence you get the sense of the depth. And that's how we see the depth using two eyes. But the chicken, they have two eyes but on two sides. So then they don't get a sense of the depth unless they move their eye and get the disparity. So this is just a hypothesis, mostly the hypothesis, but I think it's quite a nice example that you need to have multiple views or two views to see the depth. Okay, so hard life. Anyway, of chickens. So we have two eyes, and then we get the sense of the depth. And then when you give one frame, it's just one eye kind of thing. And if it moves, it's like the other eye. And then you can somehow infer the depth from it. All right, so I will quickly go through some of the mathematical details so that you will be able to eventually write the code, then just talk about these philosophical ideas and some, half-cooked concepts. Therefore, let's go through the two-view geometry, some of it at least. When cameras were invented, people had very high desire of having 3D cameras since then for like more than 200 years. And to have the 3D capturing, they also used to take two images, but seen through two holes like this, the one you can see here. And then you could also see the 3D, and then it would create the disparity, and from the disparity of the stereo, you can get the sense of the depth, and hence it would look like it's not only about 2D image, it's indeed the 3D image. So more to start how the images are captured, if we are really talking about 2D and 3D, then you must have heard about this pinhole camera model, where you have the outer wall and then the inner wall of the camera, where the objects in the outer wall, they go through a pinhole and then make the image inverted. You can just do the same thing using the lenses, and so what happens is the object inside the camera get projected here inverted, and you can mathematically represent those objects here, and then some form of mathematical formulations can be derived under the assumption that your camera is pinhole and your 3D world gets mapped onto your image plane. I guess I'll skip some details, sorry for that. By using this equation. Here, x is the 3D point, r in rotation, I guess I'll even go this one, sorry. X is the 3D point, r in t are the rotation and translation of the camera with respect to some world coordinate frame. K is the camera intrinsics, that basically has to do with the focal length. If you are using your lenses, you can see that way, that lens has different zooming, right? That's the focal length, it will zoom. And then the principal point is basically the placement of the sensor with respect to the pinhole that it forms. So this is how you can geometrically represent your mapping of the 3D point onto the 2D points. So 2D pixel basically has been projected from the 3D world X by means of the position and orientation of the camera, as well as some intrinsic parameters that has to do with focal length and then the placement of your sensor. That's how it gets mapped. So I'm presenting this because when you are measuring anything on the image, you measure P and you are interested to find X. You are interested to find back X, right? So 2D P is the 2D pixel, and then X is the 3D points in 3D. And that's what you're interested to recover. That's what depth recovery or 3D reconstruction would mean. And for that, you have to compute. In some sense, you see that, right? If I can compute M, if I know P, finding X, it just becomes a linear system, right? So if I can know the camera intrinsics and the motion of the camera, I already know P on the image, and I can solve some form of linear system to obtain the 3D point. And that's basically what it is. It's just that this particular linear system using single image happens to be ill-posed. Doesn't have a unique solution, therefore you need more than one. And then if you have two cameras, it's not ill-posed anymore, you can uniquely solve it and hence get 3D. So for that, you very quick scheme through two-view geometry, that you have one image and you have the other image, because I just told you that from one image you cannot infer the 3D. That's why these chickens are moving their head all the time. That's why you need two images. So Then you have these two images. These two images can be taken from two different cameras or the same camera, doesn't really matter. And X is what you're interested to find out, 3D point, and P1 and P2 at the corresponding point. That's very important. It's the same point on two images. We'll talk about that later. At the same time, you need to know that rotation and transfer between two cameras. So once you have rotation and transfer between two cameras, then you ideally would be able to triangulate these 2 points to obtain 3D points. So in just without the lack of generality in the mathematical settings, you are allowed to fix your whole coordinate frame on the first camera. Just simplifies things, and then you can compute the rotation. You can model the second camera's motion using rotation and translation only. And once the correspondences between these two are given, you can compute R and T. Okay. Now what we are willing to do is this. What we want to do is that I'll take this image, pass it through a network, some network, and ask it me to give X in some form as well as R and T. This is like I just give one image and then ask it, okay, give me X and it give me R and T. Well, that will not be really true. For R and T, I will require two images. So in that case, I will actually use one network that gives me X and another network that actually takes both the images, gives me R and T, right? So what I'm doing is that I'm passing one image through one network and getting X, and two images through one network getting R and T. Now I need to somehow supervise X and R and T, right? Otherwise I will not be able to train the network. So the way I'm going to supervise X and R and T is that project this X onto the second image using R and T and see if it is consistent or not. So whole thing is if it has made correct predictions on X and correct prediction on R and T, since I know relationship between P1 and P2, right? This needs to be projected exactly at P2. So you're somehow checking for the consistency, that you are only showing one image for predicting X, you are showing two images to predict R and T, and then once you know R and T and X, you are checking whether it's consistent or not by projecting X onto P2, onto the another image, and see that, okay, if P2 is the corresponding image of P1 or not. If you know the correspondences, right? If you do not know the correspondences, what you're going to do is that is the intensity at P1 is same as the intensity as P2. Are the RGB values same as two locations? And that's how you're going to self-supervise. That's the whole idea. Rest is just the details. Okay. So you could have established the correspondence this way. We are not going to establish the correspondences. We are not going to compute the motion. We're just going to use these particular settings, establish relationship, and then do the depth learning from single view. So what you are interested is feed an image, get the depth out of it. Once you get the depth out of it, you have to supervise. We supervise by doing the image synthesis. Okay. I just give you some time to read this cartoon. I think it's quite nice. Anyway, if you have any questions so far. Okay. Mic the place. Oh, mic's behind. Anyway.
Uh, so my question is, so I'm comparing like the traditional methods to compute the weight, and how can we leverage the natures of neural network and uh, unsupervised learning.
Traditional method for what? Traditional method for computing the depth, you mean?
Yeah, so so basically I'm thinking about the patch match algorithm, so which computes homography between two matches and the cross correlation. So it tries to minimize the cross correlation so that the depth is consistent between patches, and then again checks consistency between neighboring neighboring patches. So so my question is, how are we leveraging the context from unsupervised learning? Is it just to learn the homography, or so what kind of information is it learning?
So far the concept is that, okay, in traditional methods, you cannot infer depth from single view. You need more than one view to get the depth by computation, right? Now you can learn to infer from single view. If you can do image classifications, pixel-wise segmentations, and instance segmentations are all kind of complex tasks just from single image, right? Then obviously you can hope to also infer depth from single image. So the difference is that really that now you can infer depth from single image, right? That's how it differs completely. But good thing is that, well, at least from the context what I motivated today about, to infer the depth from single view, you need to understand image in some form, some abstract form at least, right? Otherwise you cannot just know that what is the depth, right? And for that, the training protocol is you only show one image, infer the depth and supervise that using more than one view, in some sense traditional depth, right? So what you could do is actually you could use traditional method to reconstruct the depth and use that as the ground truth to supervise the prediction. And more or less that's what we're doing. I might have just made it look complex. That's exactly what we're doing, but more in an end-to-end fashion. That you don't do in two stages, you are trying to do in one stage, and I'm bringing somehow the traditional method of doing the depth inference from two views or multiple. Yeah, anything else?
I think I'll have more questions later on, but we have more content to cover.
All right, let's continue. So this is also called the view synthesis, that essentially it just comes down to that you have 3D scene, and if you given the transformation between them, then you can actually project these 3D scenes and then compare the consistency across, right? Because you know where they have been projected. What exactly it's been doing is that you are it's reversing. You're taking one image, passing through a network, predicting the 3D. Now that 3D can be projected onto the image, right? If you know the rotation and translation between these two. So you predict rotation and translation between these two views, then the depth or 3D. I mean, I will be abusing this quite a lot about the depth and the 3D point, but they are interchangeable quite often, at least in our setting. So you basically are just training. In these settings, you have 3D world, and then the 3D informations get projected onto the images, and these images are located at different locations by these transformations, right? The thing that we are trying to do is to invert this process by feeding one image, predict the depth, and then warp that depth onto the other image. So when you are warping that depth onto the other image, actually you can warp the pixel values here, RGB values too, along with that depth, to synthesize this view and compare that the view that's been synthesized is same as that of that's been captured or not. And similarly, you can do on the other side. Oh, you don't even need this one to understand. You don't even need this particular part. You can just understand from this part alone. This is sufficient to understand that we are training one CNN to find 3D depth, right? And that depth, if given the transformations, can be along that depth can be used to warp this particular image onto this one to synthesize and compare the images whether they are same or not. So that's general idea I want you to understand in high level, and we'll just dig a little bit more into details now. So more in the architecture sense. So you take one target view for which you want to predict the depth. You take two views for which you want to predict the rotation and translation. And that's the network that you want to train. The concern is now, how do I supervise or self-supervise? Is that I should be able to now warp this image onto this one using the depth and the rotation and translation. That warping, the way it takes in the form is that this particular thing. Okay, so this particular thing is the capital X I discussed, because that this is in the pixel coordinate frame. You have to invert K inverse to go to camera coordinate frame and multiply by the depth. So basically, this thing is some form of your measurement cell. This is your measurement. This is your prediction, right? And then when the predictions and the measurements been multiplied together, then you get 3D points. The 3D point on the one view can be projected. This is your R&T basically. So previously I showed you this K, R, T, and X, right? So in this particular setting, I think I selected the wrong one. In this particular equation, that we are trying to relate the point and the depth from this target to the other one of the other one. So the way that you can do is this, let's call it, this is a PT, right? Can be mapped into 3D with the help of this prediction at that location, and this PT combined with the camera intrinsic K, all three of them when multiplied in this fashion, dt K inverse PT is basically X in the world coordinate frame. This is basically 3D point. That's how you can express. Now this 3D point can be projected onto this particular view, one of the view, by using this equation where this particular term is T, right? Or maybe the opposite. So then that's where this T comes into picture. And then the K is the camera intrinsics, and hence this point basically uses camera intrinsics as well as the depth been predicted, as well as the transformation that's been predicted to get mapped onto this image. Now the question is that, so my question is that, so since I know that if I have the depth and the translation, I can know where this point should be, right, on this image. Now I'm interested if I P at T this, and then if I have IS, okay, this is what is it? Let's call it this IS. ISPS. So is the intensity at this location and intensity at this location, if they are the same point, they have to be the same, right? And then the loss function becomes just the difference between these two. So those are the loss function is nothing more than ITPT minus ISPS. Some L1 now maybe. So this is the loss that you want to minimize so that the predicted depth and the predicted motion becomes consistent altogether. And that's why it's been supervised. In one way, of course, you can compute at this depth in a traditional way and directly supervised. Although you are integrating that together just to check for the consistency. Okay, so to use I mean, you can represent the depth in the disparity form, which basically in some form of inverse form of the depth. It's just for the numerical stability. That's not really important. So then it's just unit-like architectures. I don't know if you have seen it before. So there you can actually compute the depth in the multi-scales for better performance. This is not even for the idea. It's just for the core that will come along later, and then that particular network can also predict. This will take 2 inputs, and then it will predict the SE3. Basically, it's rotation and translation. So what happens is that all these assumptions that's been made is made that the world is static, but there are going to be dynamic objects, and for those dynamic objects, the equation that we have derived does not satisfy. Therefore, we need to figure out that which all paths in the image the equation is satisfied, which all parts of the image the equation is not satisfied, and that you can describe by explanatory mask, and that could be the output of the network itself. Anyway, so at the end, the previous equation that I wrote is here you make use of the predicted depth and the motion, and here is the target one, and you're just comparing the intensity values between corresponding pixels that's been derived, and that loss needs to be minimized. So in the explanatory mask is more about that you want to discount some of the pixels whenever there is high error, but you want to discount the minimum number of pixels possible. That means you want to assume that all the pixels should have the weight of 1. If it is not, you allow it to be not to be 1, but you penalize for that. So since the label for all the pixels is going to be 1, you can apply some kind of binary cross entropy to encourage that you want to reconstruct the depth of all the pixels. Again, maybe I'm skipping some of the details. The whole idea is that you want to allow some of the locations to have 0 weight. This is the weight would be 0, so that this error doesn't play a big role. But at the same time, you don't want to these weights to be 0 everywhere, and hence you want to supervise by saying that it has to be 1. And there you can compute the binary cross entropy to maximize the depth predictions in all the locations. And this is just a smoothness loss. I'm just discussing for the sake of the code that you will see that this will just assume that the depth at nearby locations is going to be similar. So eventually the network is going to look like something like this, which is unit-like architecture that will make predictions of multiple level of the depth. And then the other network that will take 2 views as an input that will make predictions of rotation and translation between views, as well as predict the explanatory mask. So eventually these 3 terms, one is to check the consistency of the intensity across the views. One is to assume that the depth is going to be smooth. It's not going to be dramatically change quite quickly. And one thing is just to encourage that you want to predict the depth in as much locations as possible. So whole idea is that all the pixels are 1 and you want to encourage the weights, you want to keep it as close to 1, but not for all the pixels, and you want to keep some discount. Okay, so if you, okay, maybe we can quickly go to through the code later. If you have any question on this regard of just 3 terms in more about the idea label, we can discuss that. Or maybe I can quickly go through the code and you can have a look into the code. The whole idea is that I wanted to encourage you to look into the code maybe later on. That's going to be quite simple, that here you can get the access to the code. You will have the link, and there are 3 loss terms: L1, L2, loss 2, and loss 3 in this line number 299 with exactly the losses that we just discussed now. One is the weighted loss of the difference in the pixel intensity. One is about that the depth must not be too different, it has to be smooth, and one about this binary cross entropy, about having depth predicted on as much location as possible. And then if you look more closely on these particular paths, that you can see that that's where you are computing the difference of the intensity values. And then if you have the, see, this is the target image. So PS and PT, basically this is the target image. This is the reference image which has been warped, and then you are taking only those valid points and then taking the difference between these two. Once the difference between these two been given, then you multiply with the expected mask, which is basically just the weight. You get the weighted differences, and then you just take the absolute mean, basically L1 norm, and call that the reconstruction loss. So this is the first term of the loss that we just discussed. Similarly, this one of the, I think, last term of the loss was the binary cross entropy, where you want to get the weights, which is this mass scale, and you want all of them to be 1 whenever possible. You just want to encourage. That's why this is like you're competing cross entropy against 1. And this is just the smoothness loss, that you are taking the second order gradient or first order gradient and then try to minimize. Just basically just want to compute the gradient and try to minimize the gradient on the special gradients, basically. So, and that you want to minimize. Once you use these 3 losses, there is a little bit more details about when you warp the pixels, then that pixel may not be on the exactly on the other pixel locations. There you need to interpolate. This is just the interpolation part. That details may not be very important for now. So once you use all those losses, 3 losses that I just presented you, you can access to that code, train that code on this particular data set. And the top one is the input image, and the bottom one is the depth, where the brighter means the closer and then the darker means the farther. And it looks not that bad. So everything is learned self-supervised or unsupervised, as you would like to call. Any question?
Okay, so as far as I understand, we are using 2 CNN, depth and post CNN. One to compute the depth and one to compute the post, right?
Can you please speak louder?
Hello?
Yeah.
Yeah. So as far as I understand, we are using 2 CNN, one to learn the depth and one to learn the post between the 2 images. And the problem here is we need to figure out is the projected point is similar to the point in the second image, right?
Mm-hmm.
For that, you have given the solution to compare the RGB values of the 2 points. So, well, that might work for the similar lighting situation, like in sequential data in the video, but will it work as well in the different lighting conditions data, like in phototourism data set?
No, that's a good question actually. Yeah, so that would not work. Then you can hypothesize that how the intensity is going to change, right? And there are some hypotheses that if intensity changes, it will have only one offset additive and one multiplicative factor throughout the image. It may change the, I mean, then that's also not very, very true and so on and so forth. So for now, we are trying to learn from the videos, assuming that there are plenty insufficient videos to learn from. And if you consider about the consecutive frames of the videos, that's often the case that the intensity doesn't really change much, right? It's not always the case, but from the empirical side, right, the experiment side, that just having that simple model already happens to work, right? I mean, this result, you can say it's working, right? And this just as simple as that. That actually means a positive thing, that even without doing sophisticated engineering, it already works. That means that the question that you are raising, if those questions been addressed, then maybe it works even better.
So if we are using just the video and just sequential data, why not to use just the best visual autometry we have and just compute the pose of each frame and just use the traditional method to compute the depth?
No, we are not interested in learning depth. I mean, we are, but maybe. So we are interested on doing unsupervised learning of the representation of the visual world. That's the one reason, right? That I want to somehow summarize my visual data in some abstract form of features that I can use for any visual task later on. Right? Just like unsupervised learning of the image classification, it's not about that I want to classify dogs and cats. No, I mean, we're done with that. I want to understand images, right? So to understand the images, you want to give a task that would require to understand the images. So inferring the depth from a single view would require to understand the image. Otherwise, there's not much of hope, right? So then we're asking it to infer the depth from a single view, which is already a good thing, that now you can just infer depth from a single view, right? But that's not the sole objective. The sole objective is that now I can maybe I can use the features learned by this network to do various other vision tasks, right? At least in the context of today's lecture, that's the case. Yes, please.
To have an understanding of the data, like if you want to have some level of understanding of the data, like say you want to learn the data, learn to predict something with a certain accuracy, so you need some size of data set, right? So to come within an epsilon accuracy, you need certain amount of data. That is generally how statistical models work. Since visual, like the scenes in our world itself are really dynamic, and I can't possibly think that we can have enough size of data. Like, how do we address that? Like, do we train it as much as possible, and for a specific task, we fine tune it to a specific data set? Or is there a way to like find an embedding or something that can provide a better understanding of the visual cues?
Well, the thing is that in unsupervised learning settings, you don't have to worry so much regarding the data. I mean, of course, not having access to data may be one thing, but visual data is there everywhere, right? I mean, you have, I don't know how much terabyte of YouTube videos, and now you can just go and watch them. You don't need labels anyway, right? So you can just keep on training your network as much as you want on all the data from the internet, all the videos from the internet in theory. Of course, there are still some complications, but the thing is that now you can just watch the videos and learn I mean, if you infer what the depth might be, you also most likely understood some visual concept already, right? So in that regard, maybe the bottleneck is going to be the computation, not the data. Right, because now you cannot just compute for every single video in the internet, right? I mean, of course, there are issues, other issues regarding that this particular simplistic framework may not really work on complex scenes, right? That so far we just assume that it's just everything is static around, and if not, then there are only a few things static and so on and so forth. But then if you really go in a complex scenes in the crowd, then Crowd is crowd because everybody is moving. Well, not necessarily, but almost all the times everybody is moving. So then it's not static anymore, right? And maybe that's what you want to understand. And there will be complex scenes and all. But this is a starting point that where now you are watching videos, right? And then making assumption that the videos are captured in the 3D world. That's the 3D world that you are living in, right? And when you move in the 3D world, these cameras are moving with 6 degrees of freedom, and then all these kind of the real world priors you are bringing into the learning framework, right? Therefore, that might be a better way of doing it. Then merely, let's say, merely predicting the future in the video, right? That you don't really bring sufficient priors from the real world. So of course there are pros and cons, but in one side you are bringing the prior of the real world that we live in 3D at the cost that that nothing is moving. Right? So on the other side, that you don't really bring the prior of the 3D world, but then you allowed everything to move. So hopefully there exists some kind of trade-off between, and maybe there are more complex, more advanced priors that, I mean, people are already doing research on. But for now, there will be some kind of trade-off somewhere for sure. But from the empirical point of view, that it looks like it works already, and then there must be only, like, space to improve, and we'll see how far we go. So by the way, this is I don't know if you guys read already. This is the map of Portugal, rotated, of course, 90 degrees. Yes, sometimes if you're not good at drawing Nepal's map, this is what happens. All right, just to address, I'll try to go quick. Try to address your question that, of course, there are problems with the dynamic scenes. If you learn in that manner, it's not going to work. And I didn't really want to advertise that so much. I wanted to stress that you can go and look into the code and run yourself and understand better. It's actually not that difficult. You can just, if you follow through today's lecture, and that's pretty much it to start the unsupervised learning of depth. Of course, it doesn't work, and then the world is much more complex. People are not rigid. People are dynamic in a flexible way, and scenes are complex. So doesn't really work. Though, so if you are clever enough, things can be done differently. So there was a viral trend in the internet. It's called mannequin challenge. You know what mannequin challenge is? You freeze yourself in a very naturalistic position and then record a video. In that video, there are people and they're static. It means all the theory that we developed so far actually is applicable to reconstruct people of various kinds. We saw that when scenes are rigid, and it's quite easy. It's relatively easy to learn depth from single view in unsupervised manner. And then if you have videos like mannequin challenge, then by definition, it's a rigid like scenes, and hence you can actually learn. And the funny enough is that since you actually infer from single view during the inference, there is nothing like rigid or non-rigid, right? Everything is rigid in single frame. Therefore, things that you learn in a very naturalistic settings of mannequin challenge, now it can be used to infer on even the dynamic scenes frame by frame, and that simply works. So those things do exist to work well. So in some parts, because I started previous lecture on saying that supervised learning works great, right? And then say that, then motivated to, then why to go for unsupervised learning. And then unsupervised learning also in some setting works really great. It does the job that it we want it to do in up to a certain extent. Just to summarize in depth learning from single view. There exist different kinds of learning methods and different settings, but the true settings of non-rigid scenes with dynamic, I mean, whatever assumption that we made about the rigidity of the scenes, that's not really true in practice. So that happens to be not been addressed so much in the literature. So some ideas and work is necessary here, and if you are interested in working on depth learning, that's the place to work. These other things are more or less done. And yeah, that being said, this particular case is what I wanted to explain, but it's not fully right. So this slide is supposed to bring two of my lectures together. That one of the domain adaptation or the adversarial learning, and the other about the unsupervised learning, and it's supposed to somehow bring them together. So let me first explain you the context, what is happening here. So in the source domain, you are given synthetic image like from the video games, and then corresponding semantics. So you can train a model that learns in the source domain from the video games, because in video games it's easy to get the annotations, right? Then you can train a model, and then if you use that model in the real world, this is the autonomous driving settings, that it does not perform well. So one thing that you can do is try to transfer the knowledge that you have learned from the source domain to the target domain, right? So it's like the experiments that you have been doing, if you are in this GAN session of the labs, or also things we discussed before, is that you can actually do transfer learning or domain adaptation to transfer the knowledge that you learn in the source domain to the target domain. There you can actually do adversarial learning or other form of domain adaptation. So you essentially are interested of addressing this problem of domain adaptation, right? So that the networks, when it extract the features on both the sides, features should look similar. That's the premise of the adversarial learning. That all being said, if you are given the video in the target, the whole idea is you don't have labels in the target, right? But you might be given videos on the target here, right? You can actually do unsupervised learning in the target. So you are doing supervised learning for semantic image segmentation in the source, and you are doing unsupervised learning for the depth prediction in the target, right? Now the idea is that these two tasks, well, I mean, you can also do the depth predictions in the source. That's not that important for now. What we are interested is this semantic prediction in the source and depth prediction in the target. Now I want to improve the semantics in the target, because I do not have any kind of supervision for the semantics in the target, and target is actually the real world where I'm interested to deploy my model. So what one can do is take help of the unsupervised learning by learning the depth in unsupervised manner in the target to improve the performance of the semantic segmentation that you learn in the source domain. So in some sense, you are largely trying to bring this benefit of learning the representation from here, right? And then trying to bring the label from here. Just learning the representation is not sufficient to know what it is, right? You cannot know what is road, what is car, what are trees, what are buildings, and so on and so forth. So for that, you need some examples somehow. Those examples that you can get from the video games like settings where it's easy to get the label. So you can just get labeled once, right? And on the other hand, you can do unsupervised learning in the target for the depth, because that can be done. You cannot do unsupervised learning really to do the image segmentation because you need the labels for that. But to learn the representations, to learn the depth, you can do that. Now, the feature representation that you have done to predict the depth can be used to predict the semantics with the help of the semantic knowledge that you learn from the source domain. So they two can come together quite well here. So that unsupervised learning for the representation, and then domain adaptations or transfer learning for the label transfer can go quite well together. And this is one of the recent work published in International Conference of Computer Vision in 2021. All right. Then the takeaway of these part of the lecture is that so depth from single image can be learned fully unsupervised. And then once you train your model to learn the depth in unsupervised method, the features or the represented learns can be used elsewhere too. And this is just an example. And then the whole idea is that many things like this can be done in unsupervised learning settings so that we have better representations, or in other words, better features. And therefore it becomes easier to do other tasks of understanding, including that label assignments using few labels, and that's what we call few shot learning, for example. Right? So that's concludes basically the part, this part of the lecture, and the applications of depth learning in itself is quite a lot, from the robotics, autonomous driving, biometrics, augmented reality, gaming, drones, and so on and so forth. We stop here with these set of slides. I can take questions if you have on this part.